the first and the last human outside low Earth orbit. So low Earth orbit is like where the International Space Station is. It's 400 kilometers away, 250 miles. And in comparison to flying around the Earth, that is like 1% of going around the Earth. And I'm using that later on because we have an idea about how big the Earth is, and going to the International Space is like going 1% or 250 miles down the road. It's not very far, so that's not very far away. So the interesting is how many human and when have we been further away? So the first we have been away is the moon. And first time we went to the moon, we flew around the moon, was Apollo 8. We didn't land in 1968. And then the last one, so that's the last one ever, was in 1972. With the space shuttle, we never went further away than low Earth orbit. And Mir or the Russian space station or any of the other human beings that have been out have not been further away than low Earth orbit. Next up, and we are getting there, where we hopefully getting back to the moon. So there is either the Artemis 3, which kind of scheduled for December 2025 to land on the moon, or SpaceX have this Dear Moon mission where they fly around the moon, so just a flyby, which they plan to do next year. But let's just say space is a tough thing, and schedules like these things here are always moving further and further out. So don't hold your breath when we get too close to these dates. But a lot of things are happening with robots. And let's take and go into that, like robots. And I'm defining a little bit later, but for the purpose of this thing here, last week we had the NASA OSIRIS-REx mission returning their payload. And this is a very good example of why we have to use a robot. So the robot here is this OSIRIS-REx that goes down to an asteroid that's a 5 football field wide. It looks a little bit wider there, but it's a 5 football field wide. It's like 500 meters. And it has this vacuum thing here. It's called, I think it's called Tag and Collect or something like that. It goes down, it touches the planet for a very, very short while, and it just sucks up 250 gram of material from the asteroid, and it sucks it up there, and then it puts it inside this module here that sits on top of OSIRIS-REx, this kind of little baby shuttle here. So it puts it in there, and then when it comes closer to Earth, then which it did, it shut this capsule off, so it went towards Earth. And OSIRIS-REx then have actually continued to the next most dangerous asteroid. The Bennu there's a weak chance it could hit us in 300 years' time. And yeah, so here you can see that they landed in Utah, and it had been collected, and it's eventually, I don't think it's flown to Houston yet, but it's going to go to Houston. The inside of this is going to go to Houston, and the next month we're getting a press release about that. So a little bit of the stats is that the average distance to the moon is 382,000 kilometers. So, going to the moon and back for our astronaut was similar to go around Earth 20 times. And the trip was a week. Bennu here, there was 6.2 billion kilometer one way, because it goes around the sun, kind of like have to catch up and fly around a couple of times. It took us a number of years to get there, and every year it's like one time around the sun. When we have to come back, we could take a shorter route, so that was 1.9 billion kilometer. But this 7-year trip is equally to 200,000 times around Earth. It will be difficult, even if this was a very big spaceship, to have any human on board this to kind of like service this thing here. It'd have to be done with a robot. Voyager, which is probably our oldest spacefaring robot, Voyager 1, is in a straight line 24 billion kilometers away from us right now. Now, it didn't fly in a straight line. It kind of like, got help from a number of different planets and flew by them and took pictures and things like that. But right now, and 46 years after it launched, is now 600,000 times around the Earth in distance away from us, just in comparison. Back to some other robots that recently have gone to the moon. So Chang'e here from China landed on the moon in 2018. Have a rover, Vikram, landed here like, I think it was 1-2 months ago. And just before it landed, the Russian Luna 25 tried to land, so it didn't, but it hit the moon. So that is a one stat. And you could also take a number of other that have actually done missions to the moon. So you can see here flyby, that's like the more easy one. That's what their moon project with SpaceX is going to be about. Going into orbit is like, flying around, more than once. Impact is to hit the moon. And that's the reason why you can see the Israeli and Japanese and now the Russians here, they have hit the moon, but they haven't landed on the moon, which is the idea is that you kind of like have a soft landing and you can operate from there. And the Japanese also had a rover with them. And of course, if they hit the moon, then they couldn't use the rover. So there's only the 4 candidates up here. Sorry. Okay, never mind. I sort of had another slide here, but there's only the 4 top 1 United States, Soviet Union, China, India, who had a rover driving around the moon. And it's only the United States that ever had a crew to the moon. And there's been a couple of return missions, which is, of course, even more difficult than just getting to the moon and then operate there. So my next point here is talking about what is a robot. So the reason I'm talking about robot is I'm saying, what is a robot versus a machine? So for many of us, we kind of like think a robot is like something like we've seen here in the background with iRobot in the movie with Will Smith. But we kind of like have to kind of like define a robot a little bit more. Let's call it not in a movie sense. And one of the things that changes that defines whether it's a robot is actually more what's happening inside the head of this robot, if I can use that term. It's how it's programmed to operate. And I have this thing here, rules versus outcome. So in this thing here, I'm going to give an example of this robotic vacuum cleaner, where you can see there's some stuff on the ground here, and there's peanuts and raisins and things like that. And consider that when you see this part here. So up in the corner, we have the kind of like the first generation of this vacuum cleaner. We had a phone app, and we have to then program that it had to follow a certain pattern. It did have like optical avoidance, but it had to be a certain size. So it will see the shoes. It will see the shoes here, but it wouldn't. There was problems early on where, for example, if a dog had a toilet visit inside, it will take the dog poo and kind of like move it around the whole living room because it thought it was dirt, and the shoes it will avoid. So this thing here needs to understand it a little bit more than just size. Now we have robots, these vacuum cleaner robot that you just put in, and then you say, go and figure out how the house looks like, and it will scan the house and will make an optimal route around the house and things like that. And it goes further with you will have docking stations where it docks automatically, and of course it empties the contents out to the docking station. It recharges the battery. And the latest one, they have also built-in floor washing capability. So there's freshwater tank, dirty water tank that you have to empty, and of course the dust from the vacuum cleaning, and fill in fresh water and things like that. But otherwise, it go around and do its own business. And And of course, it can now also recognize whether it's slippers or cable or fabric. So it have to be able to understand if it's something that is it dirt, is it a race, and it's something I have to vacuum clean, is something I have to avoid, is it maybe something I can push, that kind of stuff. And of course, it's able to kind of like more and more look in 3D to kind of like have a better understanding. And why is 3D important? Well, if you have to go with a staircase going up and down, if there's a carpet and it's, you know, how high is the carpet because it had to lift itself up onto the carpet, that kind of stuff. So more and more intelligence is put into this thing here. And the more we put the intelligence into that, we move it away from a machine and into a robot. A good example is Tesla. Yeah.
Sorry, Bjarke, sorry, we've been going for half an hour. So I was wondering, what I'd like us to do actually is, should we now pause for some questions, or do you do you want to get more into an actual example of a robot? I'm just concerned. The introduction took quite a while, but I feel we're getting into the meat of it now.
Okay.
I don't have any questions in the chat. So do you want to go through this example of that you have on the screen, and then I really think that then we need to pause for questions and feedback.
So I just want to talk about that, and then I have 2 slides more that talk about like the software part of this that kind of like tells why it becomes a robot. So I think this one here and 2 more, and then I think we can maybe end it there and then take the rest when we get more into building robots in space or building in space. So if I can just continue with this slide here. So this is a Tesla that how far they've gone with kind of like have an autonomous driving car from 2020 to 2023. It of course doesn't show anything else than just a graphic, but it was quite kind of like simple in the beginning back in 2020. And today in 2023, it's much different. Now, they are about to release version 12 of the software. And version 1 to 11 was programmed. It was like, here's a street sign and it says that, so therefore you can only drive like that. Here's a stop sign, that means you have to stop. And it was like 1,000 and 1,000 lines of code like that. In a new version 12, they've gone away with that, and they have done 100% artificial intelligence. So before they also had artificial intelligence, but that was like, recognize that sign and tell me what it says. And when it says stop, then you program lines and say, now the car have to stop. What they've done in 2023 is they said, here is 1 million videos of people driving cars. Learn from that and then start driving. There's no traditional or classical programming. So the way to look at that is that we have this kind of like in the classical programming, we have data or input, and we have answers or output, and then we have rules. So we take the input and we program with rules, and that generates an answer. Machine learning is that here's input and here's output. This is how it looked before, and this is how it looks after. Now figure out what rules should you apply in order to get that to work. And that's how the car driving is actually happening now in FSD 12, full self-driving 12 on Tesla's car. Is that they're given a lot of answers, a lot of videos of how it have to drive, and say, can you now drive like that? When you see this, when you get the inputs, when you drive around and see this thing here on the cameras, you have rules about how to turn and brake and accelerate and things like that. A very simple example of this thing here is that when we cook in traditional program, we buy these different ingredients, we follow those instructions, and then we get this roast. When it comes to machine learning, we have this ingredients, and we have this roast that comes out, and we say to listen, here's the ingredients, and this is the roast. Now figure out how to make that. And it might be that it actually can make it faster and better. And maybe it doesn't take that long time to cut the vegetables, or maybe it preheats the oven first. It cooks the chicken for 29.5 seconds because it's seen 500 videos, and it seems to get better out like that. And of course, little like before, in the example we had before here, once you have the rules, you can then actually put the rules in and have more data and get new answers out, so similar to the classical programming. But now you just take the machine learned rules and you create more and more answers out of that. And by doing that, you do this reinforcement learning. You kind of like try again and again and see, well, I changed a few parameters and now got this outcome. And now it seems to be perfect. So Judy, I think I want to stop here with the questions. What I come into in the future is that I have a little video clip about the kind of like the robot, how it is. But then the rest of the time is kind of like building and then what we need to use the robot for and things like that, which is very much, I think, what the next session about by building and things like that. So let me stop here and take question, and people want me to continue. I'm very happy to continue. Judy?
Great. Bjarke, thank you very much. And I really liked the table that you had where you showed what conditions we have to have in order for human beings versus we only need to have the electricity for the robots to be able to operate. So I really like that. That's a really nice tool for us all to use when we're looking at our ideas of what we could do in terms of developing services and products. So I'd like to open it up to the floor. Are there any questions for Bjarke on what he's covered for us?
I have a question for Bjarke, and thank you so much for walking through all of this. It's been really fascinating. You know, one of the things that teams will be doing is developing, or the main thing teams will be doing is developing products or services that solve some problem in space that we're grappling with. And I'm wondering if you could touch on, as you think about robots in space, like, if you could wave a magic wand and solve a problem that always seems to be really tricky as it relates to robotic innovation in space, what is that problem? What might it be?
Okay, so so some of the problems I find that you know, so a lot of the things that we are working on in order to go into space is, of course, in broad understanding, is kind of like life support for human beings. If we didn't have to send people to space, we could save a lot of energy on that. So a lot of the robots, like the Moxie, which is what they're testing on one of the rovers on Mars to generate oxygen, and we have a similar one that generate water by different methods suitable for Mars. All those kind of experiments are all to kind of like welcome humans to go there. So a lot of the things that we are looking at is, you know, can we grow food in space and things like that. So the thing is that half the problems are, and I wouldn't say just half, but one segment of all the problems is sustain humans on another planet. And many times that's a little bit difficult because we live on a planet where we have all this given here. Another problem I think there is that we have to look at is what it costs to do stuff in space. So, for example, if you have to do a rover, the rover will cost, you know, millions because we're only going to produce one rover. If we do solar panels, they're not going to cost that much because we have solar panels here on Earth. But if we could drive around in a vehicle on Earth that was similar to a vehicle we would buy on Mars, let's say we choose any kind of F-150 or whatever, any kind of vehicle, that we could just make airtight and was electric, because we can't use combustion engine on Mars since there's no oxygen. But if we took any electric vehicle and could drive around here, we could lower the costs. And so it is with a lot of things, batteries, all the kind of different things where we already busy with now to convert ourselves from a combustion world to an electric generated world using solar panels. Obviously, on Earth, we can also use wind. We could imagine, since there is a form of weather on Mars, we could also use that. But it's probably easier to just keep on using solar on Mars. But those different things we are considering here on Earth for electricity and transportation and things like that, we can use there. You know, if we have to live underground, and we kind of like have an idea about that doing underground, like for example, boring tunnels like they do under Las Vegas and things like that. Because on Mars, we maybe have to actually live underground because of radiation. 3D printing is a big thing, because when we send stuff to Mars, we maybe take, depending on how lucky we are, it takes between 7 months and 4 years before the planets are aligned again, so we can send stuff there. So if something breaks, it'll be nice that we could 3D print it. And we are also probably gonna send a big 3D printer to, you know, build the habitats, as I'm gonna talk about next time. Simply because we can't transport everything from Earth to Mars. We have to figure out what on Mars we can keep on using. So I think that when we think about robotics and what we have to look at the costs and how we could lower the cost. We have to look at this whole idea about programming, artificial intelligence, AI, and things like that is, of course, highly talked about, especially this year. There's lots of organizations that comes out with AI, not necessarily for space, but AI is AI. You know, if you can train it to identify things from a camera and use that to do an action, or you can do learning models and things like that, that will help us on Mars. The more we can send to Mars that's autonomous and can operate by itself, the better. Mars is so far away, so we can't remote control it. It will take 25 minutes, 15 to 25 minutes to send a command there, and the same amount of time to come back and see if it did it. If you can imagine you remote control a car and you can only figure out when you have to turn the steering wheel, and you send it like, so it had to 15 minutes later, you'll be in a complete different place when the car has to turn. So there's a lot of that kind of stuff where we have to use Earth to kind of like develop these technologies and figure out how we can benefit from them here, so we can make it cheaper if you want to go to these other planets. A good idea is also,
Bjarke,
like, for example.
Sorry. Okay, give that example. I have some questions in the chat now.
That's fine.
That I'd
the
like
last thing
to
I just
go
want
to
to say is that doing small satellites as a learning opportunity, I think, is a very, very great way of doing it, especially because many satellites is actually launched into space and the software is like not perfect. So we learn to kind of like upload the software so these satellites get a renewed life. This kind of like thinking modeling is extending the life for stuff we send into space that's otherwise very expensive to operate and get there. Judy?
Great, Bjarke, thank you so much. Carl Nielsen has a group. He has 15 senior high school students in his engineering classroom. They don't have a microphone or a camera on that computer, so they've been writing it in the chat. And so it's going to be Judy's voice of the engineering students asking their questions. One of the students has been asking Bjarke about your particular background. Just wondering what your background is, your job role, your career so far that's got you to this point.
Okay, so first of all, I'm over 60 years old. So I actually watched the Apollo program when I was a little boy, just started school. So I saw the missions to the moon landing there, and like any other kids, I'm always been interested in space. Obviously, you know, as I can see Judy actually mentioned in the chat here, I'm from Denmark and moved to South Africa 25 years ago. And neither in Denmark or South Africa, you have like necessarily an opportunity to go into space, but you certainly have an opportunity to work with space stuff. My thing is that I have been a software developer, software engineer almost my entire life. I got my first computer in the 70s and was very simple back then. And I had a university degree in software development and have been working with software almost my entire life. And I'm actually, until today, I'm still programming mostly for fun, but I have been interested in space and especially the space that we can afford to do with typically sending small satellites into to space or onto the International Space Station, or any just weather balloon or model rockets or that kind of stuff. And because of that, I developed a number of hardware chips. So in MaxIQ, we sell these X chips, we call them, where you can plug a kit together. And they were actually I developed it because I'm not necessarily super in electronics and that kind of hardware development. So I developed these things here so I can build myself electronic circuit, Lego. You doesn't know it, Lego is actually a Danish product. So, you know, as a growing up, I had Lego and I have had Lego my whole life. So I want to do the same in electronics. And I also kind of like find that, and only like a couple of years ago, got my first 3D printer. So that have got me into mechanics and design and designing some of the different things. And I find that the going to the Mars or even International Space Station, where you just can't get stuff sent there quickly, a 3D printer will do the mechanics. And my hope is my little electronics you can click together quickly and then get the software uploaded from Earth, whether you're the one or the other place, will be the electronic component of doing that. So that's my background. I think my superpower is, do you think, as you mentioned before, but my real superpower is research, learning, if I can put it that way. So I have this kind of like tenacity when it comes to research. I dig as far down as I possibly can imagine. So that's the reason why I maybe talk confident about some things that I don't really should talk that confident about. But I have been in the fields with this thing here for quite a long time. Judy, back to you.
Great. Bjarke, thank you very much. And then there was another question which was actually answered, but I'm going to read it out for you anyway. Another student was asking if the message of this presentation is that we are moving towards machine learning and AI for the future of robots being sent to space. And you certainly, in your informal part here of your presentation, you certainly did cover that. And Carl is saying, and his students are saying, thank you very much. Bjarke, we've been going for over 50 minutes. I was wondering, do you want to wrap up, or do you want to keep the rest for our workshop next week when we look at construction and building in space?
So if you don't mind, I just want to wrap up with a video clip. So this thing here, I talked about it when I answered the question. It takes 7 months if the time is right to get hardware to Mars. and 15 to 25 minutes to get software there. And of course, if it's 3D printed, it's much shorter. What I want to wrap up with is another thing that happened here last week. And it's a very good example of robots and the way we have to think about robots in the future. And I don't know if you've seen this thing here. That was on X, formerly called Twitter. So this is a robot that Tesla had developed, and it has not been programmed. It has just been used machine learning. So I've seen a lot of movies about, or videos about how to sort these blocks here. And then I learned it, and it changes, as you can see here, this block was on the side. It figured out how to put it right. It learned to unsort this thing here, and it had learned a number of different things in a few years that have been working on this thing here. And the reason why it can do that is that the computer chip, if I can call that, the computer inside this robot here is a very, very, very powerful. It's the same one that sits in the Tesla that drives around. And it needs, of course, some of that kind of power in order to do that. But my message is, as one of the questions, Julie, you were asking about, was that if we have to do robots, we have to do this kind of like way more autonomous way of doing a robot if we send it into deep space, like Mars and that kind of places. We can't remote control it, and we can't have a robot can just do like a few things. It have to think for itself. It have to kind of like figure out that when it have a task and we give it a task in a command line, that it have enough understanding of the universe it is in, seen enough videos, have enough background that it say, okay, I get your point. You want me to dig a hole? I find a shovel, I dig, and so on. It figure out what it have to do.